you hear anything?
Yep.
Okay. I'm going to turn it off for now.
Yep.
That's it?
Yeah, I think it'll set. Are we streaming and we're recording?
We are. Yeah. I'm signing my live TV soon. I'll give it to her.
Okay.
Thank you. Time for coffee?
You can't.
Is it too late?
No, it's, yeah, it's
Too
too
late
late.
to say no.
It's too late. You can do. If you want. You can talk. Okay. What do you mean? Brad's always the last one. So we gotta, oh, he's over there.
Oh.
He's here.
Still picking.
Okay, we can start. Brad's here. Okay.
Where's Justin?
All right. Well, let's just get started here. Mickey is hosting Andy, but asked me to introduce her since I have more dirt on Andy. We met a couple years ago, I guess, when it was probably soon after you started at Maryland, and just after I started here, when our respective supervisors voluntold us to do this docent teaching thing at the Smithsonian, which was, we had an experience and limited success, I would say. We got some pretty negative reviews. But we got through it. And so Andy's from Vienna. She did all of her degrees there. She's lived in the U.S. a couple times, in Seattle during her master's, and then before that in St. Louis as well. She got a PhD from University of Vienna working on some radiogenic isotope systems from Patagonia, Xenoliths in Patagonia, and then started here at University of Maryland as a postdoc working with Rich Walker, which is stuff she's going to present today. And you might have seen her around. She's been in the labs. We've been trying to kind of her come here and do neodymium isotopes, and Brad's gone there to do tungsten isotopes, which has sort of not worked out that well so far, but the next couple days will hopefully get better. And so she's going to talk about tungsten isotopes. I just want everybody to appreciate every data point here. You should appreciate, because these are some of the most time-consuming and difficult analyses that you
will
can
talk
do.
about that.
Okay, cool. All right. So I won't steal your thunder.
Again.
And
Thank you, though. All right, thank you, Jesse, for this introduction. Thank you, Mickey, for inviting me. Before I start, I have to mention a few people that had a big hand in this study. First and foremost, of course, Rich Walker, who's my postdoc advisor, and he's pretty much the main brain behind this project. Then there's Mathieu Touboul, who's done some of the earlier analyses of tungsten and who's also worked a lot on the development of the tungsten method. We've since improved it, but he's done the main work for that. Matt Jackson, who's been sending me lots and lots of samples and keeps me busy. He also puts me in contact with people that have very interesting samples. James Day also provides some of the samples. Mark Kurtz is doing helium isotope analyses at Woods Hole. Ved Lekic is from our Geology department at Maryland. He's a geophysicist, and he's helping us with the geophysical side of the interpretation of this data. Ross Heltz provided us with what turned out to be the most important samples, namely the Kilauea lava lake samples where we found the first negative anomalies. Saimi Haldorsson, who's in Iceland, he just sent me a lot of Iceland samples that you'll see data on throughout this talk. Roberta Radnick and Richard Gashnick, who's been providing samples for glacial diamictites, which I'll talk about at the end of this talk. And they've given us a lot of information. They've done a lot of work on these rocks, and they've helped with doing some pre-work before we did the tungsten on them. Okay. So here's an overview of what I'm going to be talking about. I'm going to tell you why tungsten is so interesting and why I'm spending so much time in the lab doing tungsten analyses. I'll also talk a little bit about what it takes to get to a tungsten data point, what we need to do to get some results, and why it's, as Jesse already mentioned, it's not possible to get 1,000 data points in a very short amount of time. I'll then talk a little bit about the data that's previously been published, which mainly focused on older rocks and Archean rocks. Our main project is tungsten isotopes on ocean island basalts. We've already published parts of that data, and we've since been working on a lot more on those, so you'll see more data. And at the end, I'm going to show you or talk a little bit about glacial diamictites. And this is still work in progress, but we finished the tungsten isotopes, and I'm going to show you the results. So tungsten isotopic system, the hafnium tungsten isotope system, is a short-lived system where 182 hafnium decays to 182 tungsten with a half-life of only about 9 million years. Because of the short half-life, this means that all the signatures that we see today and all the processes that led to these signatures must have taken place within the first 60 million years of solar system formation. Hafnium is a lithophile element and prefers to remain in silicates, while tungsten is moderately siderophile and prefers metal. So during metal-silicate segregation processes, such as the formation of the Earth's core, these two elements fractionate from each other. And we create two reservoirs, one the core and one the silicate part of the Earth, that has very different hafnium-tungsten ratios. And if this takes place within the first 60 million years of solar system formation, we end up having very different isotopic composition in terms of tungsten. Additionally, tungsten is more incompatible compared to hafnium in the silicate system. So during crystal liquid fractionation processes, such as the crystallization of a magma ocean, we also form reservoirs with very different hafnium-tungsten ratios. Again, if this takes place very early on in the Earth's history, this results also in different isotopic compositions. So a little bit about how we get to tungsten. So we analyze bulk rock samples. Unfortunately, the concentration of tungsten in our rock samples is very small, somewhere on the order of 10 to 1,000 nanograms per grams. But we need about a microgram of tungsten to get a good analysis. This means that we have to digest up to 100 grams of sample. And we need to purify this, so we have to put it through a bunch of column chemistry stages. So we start off with these very big columns where we can put about 10 grams through. These have a volume of about 375 milliliters, so we're using a lot of acid. We use smaller ones if we have lesser amounts of sample powder. The second stage, we put them through these anion columns, and with these columns, unfortunately, we can only put 1 gram per through one column, which means that we have to use up to 100 columns just for the second stage. We then reduce the amount of resin, the amount of acids, and the amount of columns significantly in the third stage, so we do this pretty much again before we do the cleanup stage at the very end, where we only use 1 column per sample. So it does take a long time to get the tungsten separated and get it clean enough. And once it is clean, we can load it onto filaments. And in our case, we load it onto rhenium ribbons. And with this, we then put it into our mass spectrometer, which is a thermal ionization mass spectrometer. And we analyze our tungsten as tungsten trioxide, which means we're also bleeding in oxygen. And we analyze this, one sample or one standard takes altogether about 16 hours. And during that time, our sample fractionates. So we have to do a bunch of corrections to get to our final data. So we do a tungsten fractionation correction. As I said, we're analyzing as an oxide, so we also have to account for the oxygen fractionation, which we do by measuring the O18 species with every run. So we monitor the oxygen fractionation throughout every run. And unfortunately, we are running on rhenium filaments, and rhenium ionizes at very similar temperatures than tungsten. So in combination with oxygen, we have a direct mass interference of rhenium within our tungsten. Sometimes we get fairly high rhenium signals, so we have to do a big correction on that. But we've managed to do a really good job on this, and we're not worried about high rhenium signals anymore. And you can see here that we're actually doing a really good job right now. These are standard solutions that we've analyzed, 68 in total over about 10 months. And the relative two standard deviation of these standards is 4 ppm. We're now about 4 to 4.5 ppm. And this is very important. And what you can see here is we've also analyzed a gravimetrically enriched standard solution, which we have enriched to 11 ppm tungsten, or 182 tungsten, and we do a pretty good job at resolving this. And this is very important because with this method, we can resolve anomalies on the order of 8 to 10 ppm. And as you will see, our data or our results are on the order of 8 to 10 ppm anomalies. So it's very important that we have this very good precision. Okay, no breathing. So we express our data as mu182 tungsten, which is the, we're back. Okay, which is the 182-184 tungsten ratio compared to that of a standard in parts per million. Now, previously published data was mainly, or studies were mainly focused on Archean rocks. And here is a compilation of the published data from Archean supercrustal rocks, which are basically rocks that have been deposited onto an already existing basement. They can be sedimentary in origin or volcanic. They can be ultramafic, mafic, felsic, and they are often metamorphosed. And these data, or this plot shows that most of these rocks have well-resolved tungsten excesses on the order of 15 ppm. And these are for rocks that range in age from about 3.3 to maybe up to even 4.2 billion years. Other Archean data is from Archean komatiites, or Archean komatiites in general are ultramafic mantle rocks. They have very high melting degrees and very high eruption temperatures. They are mostly restricted to the Archean. There are some exceptions, like the Gorgona komatiites that are, I think, 89 million years old, but most of them are found during the Archean. And what you see here is samples from Schapenberg from South Africa actually show negative tungsten anomalies. And this was published last year by Igor Puchtl et al. These are the first negative anomalies that have been found in terrestrial rocks. Samples from other localities show, like the supercrustal rocks, positive tungsten anomalies. And then there's Komati, which is also located very close to Schapenberg, and it doesn't show any deviation from terrestrial standards. So these, the authors that have published these papers have attributed their tungsten anomalies or these heterogeneities to different processes, such as metal silicate segregation, as in the formation of the Earth's core, silicate crystal liquid fractionation, as in the crystallization of a magma ocean, or as source reservoirs that have never received any late accreted material. So by that we mean that the silicate part of the Earth before late accretion was about plus 15 to plus 20 ppm 182 tungsten, and after the last 0.5% of the Earth's mass was added in chondritic components, which are characterized by about minus 200 in tungsten, we end up, if we mix this well, we end up with what we now consider as 0. But during the Archean, the mantle might not have homogenized completely. So there might have still been areas somewhere in the, this is very simplified, of course, somewhere in the deep mantle that still had the positive tungsten signature before late accretion. But it was thought that these signatures have since been mixed away, and that throughout the mantle mixing throughout the Earth's history has completely homogenized to some degree the Earth's mantle, and that these tungsten anomalies have since been gone. But then last year, Rizzo et al. Introduced positive tungsten anomalies, so excesses in 182 tungsten in rocks from Baffin Bay and Antonchaba, which are only 60 and 120 million years old. So they are flat basalt samples. That these flat basalts are characterized by large quantities of erupted magma, and they might be plume related, which might mean that they could have a deeper source somewhere in the Earth's mantle. So Rizzo et al. Showed that there are still these tungsten signatures that must have formed very, very early on in the Earth's history. And so we started to look at rocks that had the best potential to find these anomalies. And so we looked at ocean basalts. And why did we do that? We did that because unlike mid-ocean ridge basalts, where that result from partial melting of the upper mantle, ocean island basalts are mostly related to mantle plumes, and they're interpreted to have a very deep mantle source. And they also erupt onto young, thin oceanic crust. So we don't expect to see much crustal contamination, at least no continental crustal contamination. Sorry. Oh.
Right, yeah.
Can you hear me better now?
Yeah,
Right.
I think.
Okay, good. So we looked at, is that better? I don't. Okay. So we looked at ocean island basalts from different localities, which you can see here. Our main focus was on samples from Hawaii and Samoa. We've also looked at samples from Pitcairn, from Mangaia. We've studied a few samples from the Caroline hotspot. We've looked at La Palma from the Canary Islands. And we've also recently been doing more work on samples from Iceland. And we've added a sample from the Central Indian Ridge to represent a mid-ocean ridge basalt. So here is the data that we've collected so far. On the bottom, you see mu-182 tungsten. The gray bar, or the gray area, is the external reproducibility, so the precision that we have, which is about 4 to 4.5 ppm. And as you can see, most of the samples from Hawaii have well-resolved negative anomalies. We also see negative anomalies from Samoa. Also a few samples from Iceland. Mangaia seems to be normal. It does not deviate from terrestrial standards. Pitcairn has one sample that's actually resolved negative. And the Caroline hotspot samples look like they're slightly negative, but they're not resolved. The sample from La Palma has been analyzed multiple times with different methods, different digestions. It always ended up being around 0. And the mid-ocean ridge basalt also is 0 within the error. So we've, of course, also looked at tungsten concentrations, and we wanted to see if our tungsten concentrations correlate with the isotopic compositions. And as you can see, they don't really. We have samples that have very high tungsten concentrations, which are the Kilauea-Iki lava lake samples that have negative tungsten anomalies, and we have samples that have very low tungsten concentrations and that are also negative, and the other way around. We've also compared the tungsten concentrations to bulk rock major elements, and it looks like it's all over, but when you look at the different localities like Samoa here in blue, or Hawaii, or even Iceland, Pitcairn is very nice. They all show a trend with bulk rock major elements. And if we highlight only the samples that have negative tungsten anomalies, we don't see they don't correlate with major elements either. So we then compared our short-lived system tungsten to long-lived radiogenic isotope system, which can give us a good idea on the chemical evolution of the mantle. And we wanted to see if there are any correlations with these long-lived radiogenic isotope systems, such as osmium, lead, strontium, and neodymium. And as you can see, they don't correlate. We don't see any correlation of these systems. And I have specifically made a slide for Steve, because you asked me this at the GSW talk in January. I don't know if you remember. There.
I was going to ask you again sometime.
Yeah. So in Hawaii, there are these two parallel trends, which have different geochemical signatures. And these are also reflected in the long-lived radiogenic isotope systems. So Steve asked if we see these trends also in our tungsten isotopes. Unfortunately, there is not that much data now where we have tungsten as well as neodymium and strontium. I'm doing, I think, 7 or 8 samples right now, so I can give you better results in about a week or two. But we see with lead or with osmium, we don't see tungsten correlating with these lower Orkea trends so far.
What are the trends?
The trends? So there you see there are these parallel trends in Hawaii that have different geochemical signatures or geochemical compositions. They are assumed to have different sources. And
That major element chemistry?
that is, I'm not sure of what trace elements and isotopes.
Subtle, but yeah, it looks real.
Yeah.
The reason I asked you the question at the GSW talk is because Tony Weiss has explained that the two trends is mixing from LLDS species down to format boundary and upper level material. So what would you see,
They interpret them, those sources to be very deep as well, yeah. Yeah. But I can tell you more in a month. So we don't see a correlation with long-lived radiogenic isotope systems. So we looked at other systems, such as helium, and we found this really nice negative correlation of 182 tungsten with helium ratios, where samples that have morb-like helium, so low helium ratios of 8 R/Ra, and this is normalized to the atmospheric ratio. Those samples with low helium ratios have normal tungsten isotopic composition. Normal meaning there are no deviation from terrestrial standards. And samples with high helium ratios have well-resolved negative anomalies. So these are now only samples from Hawaii and Samoa, which is why I call this the Hawaii and Samoa trend. And we can leave the trend in the background and plot other samples, for example, from Pitcairn and Caroline. And they plot within the trend, but Pitcairn is the only sample that actually has a resolved negative anomaly. Now the problem with these localities is that there are only, in Pitcairn there's only one sample, in Caroline there are only 2 samples that have helium ratios higher than MORP, so higher than 8. So we've studied all of them, but the helium ratios are only at about 12.6 Ra. So we can't really draw a good conclusion from Caroline. We do think that Pitcairn also follows this trend as it has a resolved negative anomaly, but for Caroline it's still inconclusive, I would say. So what this negative correlation means is that we need at least 2 sources with 2 distinct tungsten helium characteristics. We need one end member or one mantle source that is characterized by low helium and normal tungsten, and we need an end member source that is characterized by very high helium ratios and also a deficit in 182 tungsten. I'm going to get back to that a little later on, but I want to show you also now the newest results for Iceland. So when we published the paper in April, we had these 2 data points. And you can't really say much with 2 data points. But we did notice that we had this, that the trend of these 2 samples kind of follows the Hawaii and Samoa trend. But it is slightly offset in 182 tungsten, where you have at similar or even higher helium ratios, the deficit of 182 tungsten is a little lower. So we analyzed more samples, which you see here. So we analyzed, count them, 7 more samples, and 6 of those samples plot really nicely in this offset trend, which I call the Iceland trend. But of course, there's one sample that does not fit the trend, which we have to say that all these newly analyzed samples, they're all one digestion, but they were loaded onto 2 separate filaments and run at separate times. So they all resulted in, they all had results within 1.5 ppm. So we're pretty confident in the data. So this is not an analytical artifact. This is, I'm pretty sure that this is real. So well, if you bear with me for a few slides, I will tell you about that. So when you have this outlier, you need to figure out why there is an outlier. What's going on with this sample? So I looked at other data, and I noticed, and Matt Jackson is doing a lot of work on this together with Saimi, and so he gave me this lead data, and I noticed that the one sample that has the greater deficit in 182 tungsten also has higher lead isotopes. And the samples that plot in the offset trend kind of plot as a group but have lower 206-204, which you see here. So if we want, because we like trends, we can see some sort of a trend forming where the samples with the higher lead isotopes have the greater deficit in 182 tungsten, and the samples that have lower lead also have a lower or a smaller deficit in 182 tungsten. And when we generally plot a field for all the Iceland samples, and these samples are all samples that have high helium ratios, that's important. And we see quite the range in lead isotopes. Now, this is all the tungsten data that we have so far. But there is some lead data for a lot of the Iceland samples. And what Matt told me and what he and Saimi saw is that there seem to be 2 high helium sources in Iceland that have, one has high lead isotopes and one has low lead isotopes, which is what fits with our data. So as you just mentioned, it is interpreted that the Iceland plume is connected to the Baffin Bay West Greenland plume. And if we plot the data for whatever is available for Baffin Island, we see that they generally have low lead isotopes. And as Hanukkah published last year, they have positive tungsten anomalies. Now, the lead and the tungsten data are not from the exact same samples, but it's a very small island, and the lead isotopes are quite restricted. So we think that we can, this is a good field for, I think it's valid to plot this field together with tungsten and lead. So if we would mix the source of the Baffin Island with an Iceland sample, with an Iceland source that has high lead and very low tungsten, we would end up with this group in the middle. So this is something that would make sense right now with the limited data that we have. Of course, we have to do a lot more work. I have to go back. Okay. Oops. Oh, this is actually a bad map for that. So Iceland is here and Baffin is over here, but this would be connected. It's a little. Yeah. I'll show you a cartoon later on where maybe it's more easier to. Okay, so what we need to do is, and that's what Hanukkah is doing, or is planning on doing, is she's going to analyze more Baffin Bay samples for tungsten, because there is very limited data out there right now. And I've already I've not analyzed, I've done the chemistry for samples, for 3 samples that are from the high lead, high helium, they have high lead isotopes. And I want to see, or I hope and I expect them to have also a bigger deficit in mu-182 tungsten, at least compared to this group, and that they all plot on the Hawaii-Samoa trend, just like this sample. And that these samples in between are really a mixture of this. Question mark. So what it means for Iceland is that we need at least 3 sources, because we need an end member source that has normal helium, normal tungsten, to create this correlation. We need an end member that has high helium and low mu-182 tungsten and potentially high lead. And we need an end member, which could be the Baffin Bay source, that is characterized in high helium ratios as well as high or enrichment in mu-182 tungsten. And to get to such reservoirs, we can form these reservoirs with different processes. Generally, I have to say that helium is considered primordial, so it's not being produced in significant quantities within the Earth, unlike helium-4, which is a decay product of uranium and thorium. So what we need to retain the high helium ratio is we need a source that has high helium to uranium and thorium ratios. And that's usually an undegassed primordial primitive source that is not enriched in incompatible trace elements such as thorium and uranium. We need also a deficit in 182 tungsten. We can create it by having a reservoir that has low hafnium tungsten ratios that formed within the first 60 million years of solar system formation. So I'm going to show you different ways of different processes that could form such reservoirs. One is by crystallic refractionation in a magma ocean, where we fractionate hafnium and tungsten. We create different reservoirs with different hafnium-tungsten ratios that end up having different isotopic compositions. Now, the problem with this is, of course, it depends on how you crystallize the magma ocean. If you start on the bottom up, or if you go from the top down, or if you go from the middle outwards, we don't really know that. But we expect if we crystallize it like this, and we end up with a reservoir that has that is enriched in incompatible elements, we also expect there to be a lot of production of helium-4, which over time would lower our helium ratio significantly. So this would give us the opposite trend of what we observe. But again, it depends on how the magma ocean actually crystallizes. A second option would be to have a core-mantle interaction. The core is characterized by very negative tungsten, and it might also have some helium in it. Now, because thorium and uranium are lithophile, they don't go into the core. So even if we have little helium in the core, we still would not produce any helium-4, so it would retain its high helium ratio. The problem with this is that if we imagine actual pieces of the Earth's core put into a mantle plume, this would have other effects, such as we need an enrichment in the highly siderophile elements. Highly siderophile elements are very concentrated in the Earth's core. So if we put a piece of the Earth's core into a mantle plume, we would expect to see these high concentrations of HSEs also in our oceanic basalts, but we don't, as you can see here. These are just, in the background are just other terrestrial samples. We have samples from Hawaii and Samoa. These include both samples that have tungsten anomalies and that don't have tungsten anomalies. And as you can see, they all have very similar platinum concentrations. So no enrichment in those elements, as we would think we would see if we had actual core contribution. Another way to form such a reservoir is from what we call stranded metal. When you crystallize a magma ocean, your melt becomes more and more enriched in FeO, and as you crystallize more mineral phases, such as bridgemanite, which is something that crystallizes in this magma ocean, bridgemanite likes to incorporate Fe2O3, so from the FeO you end up with iron metal. And this metal then accumulates and sinks down to the bottom and does not go into the core, but somehow is deposited, or is what's the word? It accumulates somewhere on a core mantle boundary. And what's important is that this metal has a low hafnium-tungsten ratio, because hafnium is lithophile and would not go into these metal droplets, but tungsten does because it's moderately siderophile. Now this all, again, has to happen within the first 60 million years of solar system formation. Now with helium, we don't know. Helium, if it does go into the metal, then it might have a high helium ratio, because thorium and uranium won't go into metal, and therefore we won't produce any radiogenic helium over time. So whatever helium is in there would have a high helium-3 or a helium-4 ratio. The problem with this is we don't really know what the HSEs would do. If we don't know what the budget of HSEs is at that point in the magma ocean, so we don't know if we would see higher HSEs in our ocean island basalts or not, but we do not see a difference. So this is an open question. There are geophysical studies on mantle plumes, and they show that the mantle plumes are always related to seismic anomalies, so-called large low shear velocity provinces, which are areas that seem to be denser than the ambient mantle. LSVPs comprise up to 8% of the Earth's mantle, and they can be found beneath all the studied hotspots. So even beneath those where we don't find any tungsten anomalies. Ultra-low velocity zones are much smaller. They are always found together with LSVPs, and these seem to be even more dense. And what's interesting is, and that's why we we suggest that the ULVCs could potentially be our source reservoirs, are because they've been found beneath all the studied, beneath all those hotspots where we find tungsten anomalies. Now they haven't been found beneath Pitcairn, which doesn't mean that it's not there. They're very small, they're hard to detect. So there might still be a small ULVC beneath Pitcairn. This is something that came out in July of this year, which shows a ultra-low velocity zone beneath Iceland. This was published by Johan and Romanowitz. And their interpretation is that this ULVC actually represents dense silicate melts. And what's important is that if they really are dense silicate melts, then they have to have formed within the first 60 million years to have this tungsten signature. Or if not, we need to have some sort of core mantle interaction. And as I said, we cannot actually we don't expect there to be an actual mass transfer from the core, but it's still possible that there could be some sort of isotopic exchange with the outer core to get the negative tungsten signature in these ULVCs. So here's a cartoon of what we think is going on, and this is a very simplified cartoon, of course, beneath Hawaii, Samoa, and Pitcairn. So we have this is the core mantle boundary. There is an ultra-low velocity zone that sits there, and there's also an LSVP next to it, and the mantle plume taps this ultra-low velocity zone, which is characterized by negative mu-182 tungsten and high helium ratios. And as it travels up, it also incorporates material from the ambient mantle, which is characterized by normal mu-182 tungsten and low helium ratios. And this is what leads to this negative correlation. For Iceland, we imagine something like this, where the LSVP is the main source for the Baffin Bay samples. This was also interpreted by Hanukkah in her paper. This LSVP is characterized by positive tungsten, high helium ratios, and low lead isotopic ratios. And we incorporate this into the plume. We also tap the ULVC, which has negative tungsten, high helium, and high lead. And a mixture of this leads then to this with also normal or ambient mantle material that leads to this offset correlation. And the sample that plots within the Samoan Hawaiian trend probably has mainly the ULVC as its source. So to conclude the ocean island basalt section is that we've seen or we've shown that we have these negative tungsten anomalies in a lot of samples from Hawaii, Samoa, and even one from Pitcairn, and a few samples from Iceland. We do not see a correlation with long-lived radiogenic isotope system, but we do see a good correlation, a good negative correlation with helium isotopes. And this correlation suggests that we have to mix at least 2, for Iceland even 3 mantle sources to get to this correlation. What's important is that this mantle source that has the negative tungsten signature must have formed very early on in the Earth's history, within the first 60 million years of solar system formation. And we can potentially connect the source to an ultra-low velocity zones that we find beneath Hawaii, Samoa, and Iceland. So we've this is a compilation of most of the published tungsten data so far. It includes Archean supercrustal rocks. It includes Archean komatiites, the phanerozoic flood basalts from Hanukkah, our ocean island basalts. We also see a couple mid-ocean ridge basalts, mid-continental rift sample. We have wolframite. We have other post-Archean samples. And what we use to determine our anomalies is we compare our data to that of standard solutions. And we assume that the standard solution is a good representation of the bulk silicate Earth. We do not know the provenance of standard solutions in general. So how do we even know that the bulk silicate Earth is what we consider as normal is 0? But when you look at samples from post-Archean samples, when you look at the mid-ocean ridge basalts, they all plot more or less at 0. And what is important to find out if the standard solution is, or if our terrestrial rock samples, our modern upper mantle samples are really 0 or normal, is by studying the upper continental crust. And to do that, we are now looking at glacial diamictites, which you can see a picture of here. These poorly sorted sedimentary rocks that are basically deposits of scrape-offs of the upper continental crust, that a glacier traveled over the crust and scraped off the material and then deposited it at certain places. And these, because they sample quite large regions, these diamictites can be seen as a good representation of the average upper continental crust during the time of the glaciation. They are also not very altered rocks, and what we can do with this is, and this is important for tungsten, to see how did the upper continental crust composition in terms of tungsten change over time. So we have studied 13 glacial diamictites. 3 of those are in North America, 1 is in South America, and all the rest of the samples are from South or Southern Africa. What's important to say is that these ages that I'm giving you, these are the ages of the glaciers. These are not the ages of the crustal components from these diamictites, but these are at the time when these sediments were deposited. And these diamictite formations were sampled in different depths, and they were then equal amounts of every sample were then combined, and that's what we studied. And we got these samples from Roberta Rudnick and Richard Gashnick, who did a lot of work on these already. And here are some tungsten results. We've analyzed our samples multiple times. We've done different digestions. We've rerun our samples. We've loaded them onto different filaments. And to make this a little more easy for you to see, I'm plotting the averages of these multiple analyses. And as you can see, the samples from the Archean are mainly negative. They have a negative signature in South Africa, with the exception of this one, which is slightly negative. All these three come from the Witwatersrand formation, so they're all from the same area. Sample from the Mosan diamictite is from the Pengola formation, which is a little bit further to the southwest, which means that it could have a different source, a different crystal source. One of the paleoproterozoic samples also is slightly negative. As I said before, these are the deposition ages. They're not the ages of the actual crustal components. So even though this is a paleoproterozoic diamictite, it might still have a lot of Archean components in it. All the others are more or less around 0. Gaub may be a little slightly negative, but it's the same. We don't know how much Archean material is actually in this diamictite. But you can see that all the other diamictites plot more or less around 0, which gives us confidence that the bulk silicate earth is really 0 and that we can use the standard solution to actually compare our samples or our signatures to. There's been a lot of work done on these diamictites, and here's a plot by Gashnick et al., which shows these refractory metals and these elements that are more enriched, especially chromium and nickel, in samples from the Archean, and that the younger they get, the less enriched these samples are in those elements. And these elements are hosted in mafic minerals. So this decrease shows a decrease in the ultramafic components throughout the time, and that the upper continental crust becomes more and more felsic with time, which is not something new. This is expected. The same can be seen from the haliosyrophile elements, where the Archean rocks have higher HSCs, or the more refractory HSCs, and then they become lower with time. So we've compared our tungsten data to one of these elements, like nickel, and we see that the samples that have higher nickel contents also have the negative tungsten anomalies. And because we like trends so much, we could say that there is some sort of a trend where we can see that with decreasing mafic components, the isotopic signatures go away or become smaller. So to conclude this, we see that the Archean diamictites show negative tungsten anomalies, most of them at least. These signatures also then disappear. After the Paleoproterozoic, we see a decrease of these signatures with decreasing ultramafic or mafic components. We do think that we can now say that the bulk silicate earth is really 0 and that we can use the standard solution as a good representation for that. And what I'm working on right now is to try to get a better idea on the actual age of the components of these diamictites, not just the age of the deposition. And we're doing neodymium model ages for that, which I'm doing here at Carnegie. I'm probably going to measure them tomorrow. And we'll also want to do some 142 neodymium to maybe get a better idea on the processes of how the source is formed. If you remember the Skalpenberg komatiites that I showed earlier that had a negative tungsten signature, they also had negative mu-182 tungsten. So it will be interesting to see if this is also reflected in the sediments. And so I have to thank a few people, Mary for letting me work in her lab and for making sure I have everything I need, Jesse and Brad for helping me, and for entertaining me while I'm here, especially. All right, well, with that, I thank you for your attention, and I'm happy to try to answer any questions.
Questions? Yes, Bob.
So thank you. There's some really fascinating potential trends here. I just want to make a comment that it seems to me your data is perfectly suited for a more multidimensional
Yeah.
things that hold you there.
Yeah. Thank you.
I have a couple of questions. So your diamictites for the Archean showed negative velocities. As far as I remember from your introductory slide, every other Archean analysis is positive. So why is there that dichotomy? Secondly, why did you choose diamictites rather than say black shales? Because you also have you reduced so custom.
Black shales are often highly chemically alterated, so we try to avoid that. All the Archean rocks that have been studied for tungsten so far are positive, with the exception of Schalpenberg, which is in South Africa. So I'm not surprised to see negative signatures in those diamictites from South Africa. It would be interesting to see what Archean diamictites from North America would do, because I would expect them to be positive, of course. So we don't really know why it's positive in North America and Russia and negative in South Africa is a strange place. It's very interesting, but we don't know why there is this difference there.
Just following on the reaction to Kyle's comment, I mean, I think it makes a lot of sense that you have, North America, you don't have a signal from things like melodic cold springs, things like they should be affecting diamictites if the source area for those diamictites was more restricted. Those Huronian ones are down in southern edge of Superior Province, very far away from those exotic terrains that might hadn't been there when the
Yeah.
glaciation occurred. So it's really going to be dependent on the source relation of the glacial material,
Yeah.
which is why you're looking at that as the next step.
Yeah.
It can be highly variable.
Yeah.
And, Conal's comment about the South African data is a good one, except that you could have eroded a terrain you don't see now.
Yeah.
Commodity formation is right next to Schottenberg, except it's not represented in that negative.
Yeah. What?
22 times.
Well, the Schalpenberg is a very strange commodity because it has very, very high tungsten concentrations, it has 10 times the concentration of tungsten that it should have. So we don't know if it's really it was interpreted to be really a mantle signature, but it kind of doesn't make sense. So whether it had some crustal component in it, and that's why there is so much tungsten, and that's why it has negative, and Komati isn't, because Komati has very low tungsten concentrations. There's still some open questions about that.
And is there any difference between the matrix and the cobbles of these diamictites in terms of tungsten concentration?
So
Rich must have studied some of that.
yeah, well, so there is within the formation there are some formations have bigger differences in the different components. Some are very similar. We just studied the composite that they put together. Yeah.
So is the connection that you speculated on for between tungsten isotopes and lead isotopes at Iceland, is that a potentially global phenomenon, or do you think that's restricted to the Icelandic environment? I think you have the low NK trend, which should be also offset in lead isotopes, but you don't see any offset in tungsten.
Yeah.
Is there a suggestion that this is an Icelandic specific phenomenon, or?
I don't know, to be honest. I don't know. I think it depends also how much other stuff you mix into this and how much you actually change the lead isotopes by adding more material from further up.
In the global compilation of tungsten versus lead isotopes, there is no correlation.
Yes, that's right, yeah. Because I think you have multiple things coming in. Well, the moon forming impact, and I've been talking with Mickey about that, is giving me a headache. And literally. No. I don't know. We don't really know when it happened, how big that body was, what the tungsten. For me, it's also important. What is the isotopic composition of the impactor in terms of tungsten? because it could be very different from the Earth or from the proto-Earth. And how much mixing happened, how much did it change the isotopic composition? There are a lot of open questions that I deal with.
So back to your Iceland data, I mean, the classical story at Iceland, which sits directly on the ridge, is the mixing between the north component coming up the ridge and the Iceland component. And can you rule out with your data offsetting that trend up to slightly higher U-182 tungsten with the north component? I mean, it wouldn't necessarily be all of them. I mean, very few morbs have been analyzed, and no morbs from there. So what if you had a morb that was slightly elevated in 182 tungsten, and you were just seeing the entrainment of that, or the involvement of that component?
I think that the
Secondary radius offset.
I think that the helium excludes that because you don't expect morph to have high helium ratios, and the Iceland samples are very high in helium. So I think that's the main problem.
Let's talk about that.
Yeah. Yeah.
So I just wanted to pick up on what John was saying, going back to the headache impact. Certainly with the recent models suggesting very high angular momentum, being able to actually mix things really well so that the moon and the Earth don't show massive variations. Your data would seem to contradict that in the sense that I think those models would not predict any massive variations.
Well, it depends when it took place. If it took place after the 60 million years, then we shouldn't see any anomalous samples. But also, with the negative data, I mean, technically it could still be a core component. So then we don't care about the moon forming impactor. But still, the positive and the negative anomalies that we see from the Archean, I guess, speak against that.
Oldest potential age of the moon is about 50
Mm-hmm.
million.
Yeah. Yeah. Close.
Okay. Yeah, and the fact that you see probably information of this tungsten is one in terms of tungsten components. I just wonder what you mean by volcanic Earth. So is it a volcanic
Yeah. Well, the entire
right now organization?
yes.
But not volcanic Earth.
Well, but
Back then.
well, there are. Yeah. Well.
Is the older crust component are getting changes or like the old entities?
Well, but that's just I mean, but if over time you produce a lot more, it's difficult to. How do I say this?
You're adding negative core material in.
Yeah.
Changing it, or if you're adding
Yeah, but it depends on the amount of how much is. I mean, we tend to like to go for samples that we potentially can find anomalies because these are the interesting ones. We don't know how much there is actually that is normal. So if we analyzed all Paleoproterozoic through now, with maybe the exception of the ocean basalts that have a very small source somewhere very deep, we would probably see a lot of normal tungsten concentrations.
Thank you. That's great. I learned a lot. But I got a bit confused. So, so in the first 60 million years or so, there are some heterogeneity forms. Some have the positive anomaly, some have negative, and maybe later on there was the interaction between core and mantle, and so they're spatially different. But over time they were like slowly mixed with each other. Is that the picture you have, or?
My picture changes. I mean, but then there's the moon forming impactor. Then there is the core. We don't know exactly how this magma ocean crystallized. There are a lot of things that, unfortunately, a lot of unknowns that are troubling.
Questions? We'll let Andy off the hook. She'll be around this afternoon and probably tomorrow, I think, if we're running on through drummer. Thanks again.
Thank you.
Can I have your slides later? Oh, can I have your slides?
Sure.
I think it's very educational. Very educational.